Day 132, Honors Physics, problem number 24, electric fields due to point charges. In this problem, we have three given charges. We have a 3 microcoulomb charge right here, which is 20 centimeters from this negative 6 microcoulomb charge, and collinear to those two is this negative 9 microcoulomb charge, which is 20 centimeters further, so that the negative 6 microcoulomb charge is halfway between the other two. So I've drawn here for you the field vector directions for each of the three fields that are created from each of the point charges. So for example, E sub 1 here would be the field vector that's away from this charge. So there would be radial outward electric field from this charge in all directions, but all I care about is the one direction going along this line straight out away. And I could put all three of these on top of one another. Technically, that's what I should be doing, but then you wouldn't be able to see them. But E sub 3 here then would be the E field due to this 3 microcoulomb charge. And you can easily calculate that using the following equation, as you've seen in class. E equals KQ, which is the source, which is 3 microcoulombs in this case, divided by R squared. So that's our general equation. So E sub 1 here would be 9 times 10 to the 9th times that charge, 3 times 10 to the negative 6th, divided by the distance from the 3 microcoulomb charge to the point of interest, which is point A, as listed in part A of this problem. This blue dot is halfway between the plus 3 and the minus 6 microcoulomb charge. So that is, according to the given information, 10 centimeters, which is 0.10 meters squared. All right, so that would give you E sub 1, the field vector due to the 3 microcoulomb charge at a location 10 centimeters from it to the right at that blue point, point A. So so I'll let you do that. I'll get you E sub 1. All right. Now, what you will have to do after that, you'll figure out E sub 2. E sub 2 is toward the negative 6 because electric fields are towards negative charges and away from the positive charge, as you saw for E sub 1. Now, the thing about E sub 2, you can take a shortcut. Once you have E sub 1, and you'll have a number for that, a magnitude, and we know the direction is to the right, E sub 2 will be twice as big. So all you have to do, you don't need to recalculate E sub 1, E sub 2, just take E sub 1 and double it, because the only thing that changed is the same distance. It's the 0.10 meters, it's 10 centimeters, but 6 is twice the magnitude as 3. So you take E sub 1, double it, that gives you E sub 2. And now for E sub 3, you can calculate it if you want to play it on the safe side. E sub 3 would be 9 times 10 to the 9th times the, times 9 times 10 to the negative 6, because we're calculating the electric field now due to that 9 microcoulomb charge way over there to the right, but it's 30 centimeters from point A, and you square that. That'll give you a value for that number. So you could go through all that. Once again, though, if you're really savvy with the math, once you have E sub 1, like I said before, E sub 2 is going to be twice as large as E sub 1. But E sub 3, in a sense, is, in one aspect, will be 3 times larger due to a 3 times larger charge. That would tend to make E sub 3 3 times larger than E sub 1. However, there's a reduction because of the distance. It's 3 times the distance. So in 3 times the distance, when you have an inverse square relationship, that would give you 1/9 the strength. So the net result is, for E sub 3, 3 times larger than 9 times smaller, it ends up being, net result, 1/3 of E sub 1. So that would be the shortcut you could take, or you could just multiply like I have down here. Just take this whole equation right here and calculate it. It's going to come out 1/3 of this value right here. Once you have all three of your vectors, E sub 1, E sub 2, E sub 3, just add them together to get your net electric field at location A. There's nothing there but empty space, but that's the field strength at that point, and the answer would be directionally to the right. So I have part B now drawn out. We have your 3 collinear charges, and now you're at location B, which is far to the right, or 20 centimeters further right from the negative 9 microcoulomb charge. But once again, all three of these charges independently will create a field that will then have to be vectorially added when the problem at the end of the problem. So due to this charge, there's a radially outward electric field this way and up and every direction, but if I go all the way along this way, this E sub 1 that I have labeled here is due to that 3 microcoulomb charge. And then I have it written down here. It's K, the Coulomb's constant, times that 3 microcoulomb charged, divided by the total distance from the 3 microcoulomb charge to point B, which is now 60 centimeters, because the charges are 20 centimeters apart, and point B is 20 centimeters even further than the negative 9. So that would give you E sub 1. Then what you would need to do in this problem, I've got the directions already on here. E sub 2 would be the field vector due to the 6 microcoulomb charge. What you would do to figure out E sub 2, it's going to be a little bit stronger than E sub 1, because first of all, the charge is twice as big. So instead of a 3 here, you'll have a 6. And you wouldn't put the negative 6 here. The negative is already taken care of with the directional arrows, but you'd put a 6 here where the 3 is, but the distance would be 0.40. So that's going to help make E sub 2 stronger than E sub 1 as well. That'll give you E sub 2. And then E sub 3 will be a huge vector, because you're going to have a huge charge. So you just change this 3 to a 9, and this distance to 0.20, very close distance, squared. That'll give you E sub 3. Once you have all three vectors, the way you combine them by vector addition is you're going to add the 2 and the 3 together because they're in the same direction. We don't have to worry about components here, because nothing is really at an angle here. Everything is linear left and right. So we add to the 2 and 3 vector, just arithmetically, and then subtract the E sub 1. And the final direction will be to the left, because those two together will be much stronger than the E sub 1 to the right. That will give you the net result at point B.